Okay, so welcome back. As I said, both in the announcement and the earlier announcement and in the chat just now, if you have questions about the homework, you can post them in the chat, and I'll try to answer all of them in the last like 10 to 15 minutes of class. Anything I don't get to, or anything, if people weren't around to ask questions, I'm going to hold office hours later from like 2 to 3 ish. And if there's enough discussion that happens during office hours, I will make those public on the YouTube as well. That way, um, those who didn't make it to them can at least see some of those explanations. Got a ton of questions about the little converse little des arg, and the reason why it's confusing is because the statement itself is a little confusing, the way that it's written in the textbook, and the way that I wrote it when we talked about it. The issue is that the way that it's written is written in a way that is slick in English, but if you were to write it logically, as a logical statement, it's a little confusing the way that it's written because one of the things that looks like an assumption is actually a definition of an object that you're talking about. So anyway, I'll bring that up later. That's the main thing. And yeah, so I'll answer all those questions. I didn't read the longer thing here. Like I said, I'll have a look at that in a few or near the end of lecture. Okay. So anyway, last time I was starting discussing the notion of spherical geometry. So spherical geometry, as I mentioned, was actually an ancient known example of a non-Euclidean geometry, but it wasn't considered non-Euclidean. Like basically none of the mathematicians that encountered it, up until the modern era, even like noticed that it was an example of non-Euclidean because, as I mentioned last time, we think of this sphere. I'm not gonna draw this in pen because I want this picture to look nicer, but you can imagine we imagine this sphere sitting with its center at the origin in R3. The idea was that R3 itself was a Euclidean space, and so any geometry that we're doing on the sphere is really Euclidean geometry, even if after we do all these restrictions, it is clearly non-Euclidean in the sense that it doesn't follow the rules of Euclidean geometry. And I'll go over a few of those examples that you might already be aware of. So really the problem here was that because it already sits in space, it was considered like Euclidean inherently. Okay, and RP2, it doesn't sit in space in the same way as the sphere. The sphere literally, is sitting in space, and in fact, as we'll see, if we're doing this Kleinian, Erlangen program approach of looking at the transformation groups of the sphere, we'll see that the isometries of the sphere are actually restrictions of isometries of R3. So that even more makes it look like, oh, this is really like Euclidean geometry that's going on, even though it's not. So that's one thing, right? And so that was the reason why it wasn't seen as such, but it very much is a non-Euclidean geometry. And to see that, first we define the points, right? So what are the points? Well, the points in spherical geometry are just points on the unit sphere, or of course we can talk about a sphere of any radius, and the geometry is not really gonna change for the notions that we're going to talk about, but points on, say, unit sphere that we'll call S2 in R3. Okay. So what is S2? Right? Well, first of all, I can draw these points. So here's a point on the sphere. Here's a point on the sphere. Here's a point on the sphere. Here's another one. Here's one. Right? These are all points on the sphere. Okay, so our points are just normal points lying on the two sphere. Why is this called the two sphere? Well, we'll see here in a second. So first of all, my points on the two-sphere. Maybe I'll write S2 as an actual set. So this is the set of, points x, y, z and R3 such that they're equidistant, they're distance 1 from the origin. Right, so that's saying that it's a unit sphere centered at the origin. So this is a set of all points such that x squared plus y squared plus z squared is equal to 1. Okay. All right, so this is called the two-sphere. This is the two-sphere in R3. And even though those of you that don't have too much familiarity with doing a lot of work on the two-sphere might inherently think about it as a three-dimensional object because it sits inside space. This is a surface in space, and it's a really, really nice example of a surface in space. So it's two-dimensional. And the reason that it's two-dimensional is because I only need two real parameters to describe a point. Right? This is two-dimensional. So this is two-dimensional. Right? Only latitude and longitude are needed. You can call them that, right? It doesn't matter what you call them. I only need two real parameters to describe a point on the sphere, right? So only latitude and longitude are needed to describe any point on the sphere. And so another way of viewing this, if you're an algebraist at heart, is that this algebraic condition on the points of the sphere actually reduces the amount of freedom you have, right? So a typical point in R3 is represented by three real parameters, x, y, and z, we'll say. So then this condition, that x squared plus y squared plus z squared is equal to 1, actually reduces one of your degrees of freedom here, right? So now you only have two real parameters that are required to describe any point. Okay, an extra one would be redundant here. Okay, and so my points are just the points on the normal sphere. Okay, it's a two-dimensional geometry, just like R2, just like RP2, right? Just like the projective planes that we had to look at, like the molten plane in your homework. These are all two-dimensional. This is plane geometry of some type, so it's two-dimensional geometry. The points are the normal points on the unit sphere, and the lines are great circles. So great circles on the sphere. Now you already know what great circles are. In fact, I've already drawn an example of one, right? The equator of this sphere is an example of a great circle. A great circle is an intersection. I wrote this last time, but it's the intersection of the sphere with a plane passing through its center. But its center's the origin, so it's a plane passing through O. Right, its center. And so there's many examples of great circles. So if I tried to draw something down here like this, that wouldn't be a great circle because it doesn't. It's not an intersection of a plane passing through the center. It'd be an intersection, right? The cross section of a plane cutting the sphere down here, not passing through its center. Here would be another example, right? And so lines are great circles. Line segments would be arcs of great circles. And intuitively, if you've done any kind of work with this before or just thought about it kind of as a neat thought experiment, the shortest distance between 2 points on a sphere is along an arc of a great circle, right? Of course, already there's a lot of things that are weird about the sphere. So one, you might notice if I have antipodal points, right? All of a sudden, questions about the uniqueness of lines between points or line segments between points fail, right? Because if I have antipodal points, well, you see there's an issue here, right? In fact, you can say here's one arc of great circle, here's another arc of great circle. So I have two different arcs of the same great circle that would yield a shortest path here. There's a lot more depth that I could go into with this, but unfortunately it would take us kind of out of the realm of this course. And unfortunately, it is maybe like it's an unlucky fundamental truth of the universe that geometry is a tricky subject because it requires so many branches of math. And to develop the foundational stuff so that we could talk about this in the way that we talk about analytic geometry when you're thinking of like what you're doing in calculus, like in Calc 3, for instance, right? The type of geometry you're doing. If we want to develop that fully to be able to discuss an example like the sphere in detail, it requires a lot of effort, and it didn't come until way later. So it came, it came right around the same time that all of this Klein stuff was coming, but it's kind of, it would require me branching out a little bit too much. So unfortunately, we can't talk too much about it. If you want to see that, this is the content of Math 436. So when you get to surfaces in Math 436, then you're talking about exactly this sort of thing. Okay, and anyway, so there's my points. My lines are great circles. Already, to show you that this is non-Euclidean, I kind of already have, but let's just do it in another way. So I've said that my line segments are arcs of great circles. Okay, and so it would make sense to define a triangle to be 3 line segments, just like it is in the plane. Maybe I'll trace it out with a different color. So here's one line segment between those 2 points. And here's another. And here's another. Now, I wasn't able to color on the line there. Okay. I just drew a triangle in this way that has 3 right angles. Okay. Now you might complain and you might say, wait, right? Angles are only defined between 2 straight lines, right? And on the sphere, you can't even have straight lines, so you can't even talk about angles. But it's not true. We can define a notion of angle between these things that we're calling lines. So it turns out that what we're doing here is that we have generalized the concept of a line by saying, what is it that's important about a line, right? It's straight, right? A line is straight. What does it mean to be straight? So I think it's useful to go through this. It's a little aside here, kind of justifying why we can do this. So the idea is that what makes a line in R2 straight? So now we are going to step outside what we've been doing in this course, and we're going to bring in some knowledge from elsewhere here. Right? We're going to bring in some forbidden knowledge. We're going to bring in some calculus here. What is it that makes a line in R2 straight? I'd say the fact that it doesn't turn. What does it mean if a line doesn't turn? One way of saying that a line doesn't turn is, let's say that gamma of t parameterizes a line. So we'll say this is a line, okay? And the line is parameterized by a function of t, of a real parameter t, gamma of t. All right, so if this parameterizes a line, saying that a line is straight, or that it doesn't turn, is the same thing, and you can think about this a little bit, as saying that its second derivative is 0. Okay. Now, if its second derivative is 0, what does this mean for this line? Integrate, right? Integrate this, and I get that gamma prime of t is equal to some constant that I'm going to call m. Okay, so m is a constant. Right? You integrate 0, you get a constant, so m is just some real number. Okay, integrate again, and gamma of t is mt plus some other constant that I'll call b. So m and b are both just real numbers. Oh, but look, right? What do we get? We got the description of a line, right? This is our normal equation of a line, right? This is the equation of a line. And so this is another way that we have spat out geometry from somewhere. In this case, it's from analysis or calculus. Now, the thing is that this is a little circular because in order to build the calculus that we talked about, there's a lot of underlying assumptions and stuff that go in there that are actually more powerful than the stuff that we've assumed for our geometry, or like Hilbert's axioms or something. So basically, it's a little bit circular, but this is to show that if you start out with the assumption that a line is a thing that is straight, doesn't turn, and if we use the normal interpretation, right, either from physics or just intuition, that being straight means second derivative is 0 in the plane, then this is what I get. I just get the equation of the line spit out. So anything that satisfies this has to be a line in this way. Okay, and now, why did I bring this up? The idea is a straight line in a more general space, and we'll call our straight line gamma of t, satisfies some differential equation. Okay, we call this differential equation the geodesic equation. And if it satisfies this differential equation, it is called a geodesic. Okay, and so what we're doing is, this is a fundamental notion in what's called Riemannian geometry, named after the mathematician Riemann, right? Same guy from Riemann sums. So this is the notion, fundamental notion in what's called Riemannian geometry. You will see the Riemannian geometry restricted to dimensions 2 and 3, or 1 and 2, if you take Math 436. So basically, Riemannian geometry in dimension n equals 1 or 2 is done in Math 436. And unfortunately, if you want to see more than that, that's a graduate level thing. The geometry is kind of complicated like that, sadly. Well, I shouldn't say sadly. That's what makes it interesting, right? But anyway, the reason it's called a geodesic and we don't just keep saying line or straight line is it's confusing, right? And the reason it's confusing, going back to our picture here, is that these straight lines, right, these lines, they coincide with actual lines in space. The problem is, as I mentioned last time, is that if I were to draw the line between these two antipodal points on the sphere, what would that line look like? It would be this line passing through the middle of the sphere, but that's not allowed, right? I live on the sphere, not inside the sphere. The sphere is just, the sphere itself, right? It's the boundary of the three-dimensional unit ball. Okay. And so anyway, like I said, here's a triangle. This is actually a triangle. It's fully sensible to call this a triangle. It has 3 right angles. Clearly something that is not allowed in Euclidean geometry, right? And so this is definitely an example of non-Euclidean geometry. Now, we're going to understand why mathematicians didn't consider it a good example, or even consider it as a challenge to Euclidean geometry at all, which is pretty funny, right? Because it's a pretty extreme thinking about those concepts in that way, it's a pretty extreme example of a non-Euclidean geometry. But because it sat in R3, it was just not seen as being truly non-Euclidean. Okay, so what are the isometries? So what are isometries of the sphere S2? So the reason why we're saying isometries of S2 is to be clear that, we are concerned with maps that preserve some quantities we care about on the sphere. Okay. Well, it turns out that our isometries are going to be the isometries of R3 that leave the origin fixed. These are isometries of R3 that leave the origin fixed. So this immediately rules out some isometries of R3. Right? So this definitely rules out translations, right? Non-zero translations are not allowed because they shift the sphere, they shift the origin, so that's no good. But ones that leave the origin fixed are fine. Okay. All right, and it turns out those are exactly the isometries of S2. Okay. So we're using the word isometry because the main thing we wanted to preserve is distance. So by definition, if F is an isometry of S2, right? We can view this as F maps from S2 to S2. Then it preserves distance. Okay. Thus, if F leaves O fixed, right? Maybe I should actually here. Let's start out with F being an isometry of R3. So let's say that F is an isometry of R3. So rewriting this, F maps from R3 to R3. Okay. All right. So it preserves. This is just our original definition of isometry of R3. Then if F leaves O fixed, right, then it sends each point of distance 1 to the origin to some other point of distance 1 to the origin. Because it preserves length. Right? So it maps from S2 to S2. Right? i.e. F maps S2 to S2. And thus we can think of this as restricting to S2 in this way. So thus, the restriction of F to S2. What is a restriction of a function? You might remember this if you've had 410, you know this well. If not, then a restriction of a function is when you have a subset of its domain. Restricting that function to a subset of its domain just means basically you're considering the same function with a new domain being that subset. Okay, and so the restriction of F to S2, we write that as F restricted to S2. I don't think this textbook uses that notation that much, but this is what the notation looks like if you see it anywhere else. So thus the restriction of F to S2 is an isometry of S2. Okay, because it preserves distances on S2 just like it does everywhere, right? It preserves distances in R3, so in particular it preserves distances in S2. So then restricting it to S2, it's a map from S2 to S2. Okay. All right. And so what is funny is you might say, well, but in one case, the distance that I'm talking about is distance in the sense of R3, right? But if I'm talking about it being an isometry of S2, I clearly want to think about distance in the sense of S2. And distance in the sense of S2, what is that, right? If I bring back my sphere here, distance in the sense of S2 it's like, what's the distance from this point to this point? Well, it can't be this normal distance, right? Because that's not allowed. That's not a distance that you can traverse in S2. All right, it would be the length of this thing, right? The length of that arc of that great circle. Okay, that would be the distance. Now I can measure that, of course, as an angle. Okay, but it actually doesn't matter. It actually preserves it in both cases. Whether I talk about distance in R3 or distance along S2, it's preserved in both cases. So that's all I'll say about that. So then, what are the isometries of S2? Getting back to this question. Maybe I need a new sheet here. So the isometries. What are they? Well, there's some simple ones. There's there's if we now understand that an isometry of R3 that fixes the origin is an isometry of S2, then we should just consider different cases of isometries of R3, right? So the simplest isometries of R3 that fix the origin are reflections in planes through the origin. Okay, so the simplest isometries of R3 that fix O are reflections in planes through the origin. You might be a little bit confused here, right? You might be a little bit confused because you might think, like, intuitively, wait, isn't like the simplest thing you could do as an isometry of R3 some kind of rotation, right? But now keep in mind that rotating in R3 is a little complicated, right? In R2, rotation is easy to understand. But in R3, if you're going to take that sphere and just rotate it, like in fact, I actually was supposed to have a sphere that I could draw on, but it was out. So I wanted to have a sphere that I could put like a marker on and erase to actually show some of these things, but wasn't able to get it. But anyway, like if you hold, a sphere in your hand and you turn it while keeping the center exactly where it is, right? Like intuitively, that's easy to understand what's going on there. But if you actually try to describe those rotations, it's hard. So we'll see that there's a way that we can talk about space rotations that is actually very simple, that involves quaternions. And anyway, so that's one thing. Okay, so then these reflections in planes through the origin are actually the simplest. Of course, if they're reflections in planes through the origin, intersections with those planes through the origin and the sphere itself are what give you the great circles, right? So i.e. the corresponding isometries of S2 are reflections in great circles. Okay. What's going on here? So say that two planes, say P1 and P2, meet in a line, say L, through the origin. Right? Two planes meet in a line if they meet. So say we have two planes, they meet in the line L through the origin. I don't know why I wrote it as script O. Let's just write it as O so there's no confusion. Okay, and the product of reflections in P1 and P2 and P1 and P2 is a rotation about L. What kind of rotation? It's through twice the angle between the planes. All right, so when two planes meet in a line, they meet at an angle. You can imagine that, right, as sheets of paper that could pass through one another. If you have two sheets of paper that can pass through one another, you arrange them in such a way that they meet. Well, they meet at some angle that can be defined, and the rotation about L is through twice that angle of intersection between the two planes. Okay. All right. This is actually very similar to what happened when we were just in the plane, right? So the situation is almost identical to what happened in R2, and the product of reflections in R2 is a rotation, right? Recall in R2 that the product of two reflections was a rotation. Well, right, that was one of the things that it could be. Right. Okay. So if you had a product of two reflections to the origin, it was a rotation, and it was a rotation through twice the angle between the lines, right? So it was a product of two reflections, say through the origin in R2. It was a rotation, and the rotation was through an angle, or twice the angle between the lines of reflection. Okay, and so in this way we get a rotation about the line L. Okay. Okay, so lastly, one more thing to consider. There are products of reflections in three planes that are different from products of reflections in one or two planes. Okay. Okay. So then what happens here? So there's many examples of this, but the one key example is the antipodal map. So one important example is the antipodal map. Okay, what is the antipodal map? It takes a point on the sphere x, y, z, right, and sends it to the point minus x, minus y, minus z. Okay. All right. To see how we come up with this map, so the antipodal map is, another way of describing the antipodal map, let me just bring it back for a second, is that it sends a point to its antipodal point. Right? So it sends the North Pole to the South Pole, and so on, right? It sends a point on the sphere to its antipodal point. Okay. Now, the antipodal map, so the antipodal map is a product of three reflections. So which three reflections? So one reflection in the YZ plane. What does reflection in the YZ plane do? So that sends a point XYZ to the point minus X, YZ. And then reflection in the ZX plane which sends a point xyz to a point x minus y z. And then lastly, reflection in the xy plane, which sends a point xyz to x, y, minus z. So it's a product of these three, right? Okay. It turns out that there is a three reflections theorem for S2 just as well as there was for R2. Right, so any isometry of S2 is the product of one, two, or three reflections. One, two, or three reflections. Okay. The proof is actually similar to how we did the proof for R2. And this automatically gives you the fact. So this yields the fact that every isometry of S2 is a restriction of an isometry of R3. So this on its face kind of sort of looks like some vindication for the people throughout the years that didn't quite view this as a proper example of a non-Euclidean geometry, because, well, it's somehow like included, like it's somehow a subset of Euclidean geometry, even though that's not quite the correct way of viewing it. Okay, spherical geometry is absolutely a non-Euclidean geometry, but because it sits in R3, there's this issue. There's this issue of not properly giving it its due of being, non-Euclidean. And so the main thing I mentioned before, the reason why the mathematicians at the time didn't have the understanding to recognize that it was truly different was when mathematicians studied curves, surfaces, higher dimensional spaces, the idea was that these things sat inside an ambient space. Okay, and the problem with this is this gets a little confusing because you start to wonder if it matters how they actually sit inside the space. So, for instance, does any geometry that I want to do on the sphere, is it like dependent on how exactly the sphere sits inside R3, right? How exactly the sphere sits inside space. And so this caused mathematicians to develop notions of what were called extrinsic geometry versus intrinsic geometry. Okay, intrinsic geometry was like the geometry of the surface itself. If I try to pretend that nothing else exists except the sphere, and there is no ambient space, then the geometry that results from that is this intrinsic geometry, right? It's like there's nothing outside the sphere. Extrinsic geometry then would be this geometry that I view as I'm imposing as, coming from the fact that this thing sits inside R3. And there was a big thing proved by Gauss called the Theorema Egregium. This is one of the things that you will prove in Math 436 if you take it. So this is the remarkable theorem. And what the remarkable theorem says, I'm not even going to write it down, I'm just going to say it. So what the remarkable theorem says is that there's no such thing as intrinsic and extrinsic geometry, that it's the same geometry. So it actually doesn't matter how the thing sits inside the space. You can just forget how it sits inside the space. In fact, you can throw the ambient space away. Maybe I'll say that. You can toss out the ambient space. And so what does that mean? It means that when I'm considering the sphere, notice that I actually, when I drew the sphere here, I drew it in a way that I didn't draw in my axes. And that was on purpose because the idea is that once you know the theorem of egregium, then when you look at this sphere, you don't have to consider it sitting in R3. You can pretend R3 doesn't exist at all. I need two real parameters to describe any point on the sphere. The sphere doesn't sit inside R3. It doesn't sit inside anywhere. It is all that exists. The entire universe is this sphere. There's nothing else outside of it. Once you do that, then it becomes intuitively clear why this is truly non-Euclidean, because the geometry of the sphere doesn't rely on the fact that it sits inside R3. That this geometry that you get is something that it doesn't it doesn't get from R3 in some Euclidean way. It doesn't taint it and make it somehow Euclidean just because to define the thing we considered it sitting inside R3. That's the idea. Okay, so in the last few minutes that are left, I got like roughly 9 or 10 minutes left, I wanted to address some questions about the homework. So first of all, let's discuss so homework 5 questions. So homework 5 questions, I want to discuss the Little-Desargues theorem and talk about what the converse to Little-Desargues theorem means. So I'm not going to write it, I'll just put it on camera here. So Little-Desargues theorem says, if two triangles are in perspective from a point, called P, and if two pairs of corresponding sides meet on a line L through P, then the third pair of corresponding sides also meets on L. Okay. Why this has caused a lot of confusion is that it seems like in the forward direction here, we have two if statement assumptions. Okay. If two triangles are in perspective from a point P, that's definitely a nice, meaty assumption. And if two pairs of corresponding sides meet on a line L through P, where is the assumption here? This has been the confusing thing, because what many of you have tried to do is take what follows the if as one entire assumption here, which leads to strange attempts to formulate a converse to this statement. Okay, so the two pairs of corresponding sides meeting on a line, that's not an assumption. That always happens, right? That's the definition of the line L. Okay. So the fact that you have two pairs of corresponding sides meeting on a line L, that always happens. To show you that always happens, well, just draw two triangles. And in this direction, you can even draw them in perspective from a point if you want, but draw two triangles, right, and draw the pairs of corresponding sides, right? And the idea is we're in projective geometry, right? So even if the two pairs are both parallel, like pairwise parallel, then they would meet on a line at infinity, right? We don't care. But if they're not, right, those two pairs of corresponding sides would meet at 2 points. Those 2 points determine a line. We call that line L. So the fact that these two pairs of corresponding sides meet, that's not an assumption. What's the assumption is that the line L they meet on goes through P. Right? That's part of this assumption. Okay. Then the third pair of corresponding sides also meets on L. And of course the picture, if we look at it, looks like this. Okay. Okay. And so, what is the proper way to formulate converse to this statement? So converse of Little-Desargues. So we had this, maybe I'll go back to see if you can see that. There we go. All right, so I know that some of these intersections can be kind of hard to see. I'm looking on my screen now. Looks like you can see them all if you really look close. So yeah, if you really look close, you can see them. You can see the dotted lines here, and you can see the gray lines and the solid lines. Okay. So what's the difference between little Desargues and big Desargues, right? Just normal Desargues. It's that for normal Desargues, we don't have this, point being restricted to being on this line. The point could actually be wherever, right? For Desargues. Okay, so that's the difference. So little Desargues is a special case of Desargues. It's where you're restricted to the point actually being on the line L. And so what's a proper converse for little Desargues? Well, if we look at this picture, little Desargues says that if we are in the situation that we have two triangles, these gray triangles, in perspective from point P, okay, then these two, say, pick two of these pairs of corresponding sides. We'll pick the solid and the gray. Okay, so the solid and the gray, they meet on a line L, and that line L passes through P. Okay. Then, in that setup, the last pair of corresponding sides that we didn't consider before also meet on L. Okay. Now, again, this seems really weird, but we're using the first two pairs meeting to define the line L. The statement is not that the two pairs of lines meet at a special place. It's that they meet on a line that passes through P, right? But them meeting is not part of the assumption, as I said, because any two pairs of corresponding sides of a triangle are going to meet on some line, right? Okay, so what's important there is that this line passes through P. Okay, and so in that case, we're guaranteed the third pair have to meet on the same line. So then what would the converse, right? Following how we formed the converse of little Desargues. So we did converse of little Desargues. If you wanted to look at the converse Desargues theorem, this is in 6.3 when we talked about this. I can't remember. I want to say I proved this. If I didn't prove this, maybe I didn't prove the scissors theorem, but I proved, I'm pretty sure I proved this when we did it in class. I think this is one of the lectures I did when I was sick. So here's the converse Desargues theorem looks like this. Okay, if corresponding sides of the two triangles meet a line, then the two triangles are in perspective from a point. So it was easy to formulate the converse. Okay, the proof of this, of course, relied on Desargues. Okay, now our proof of the converse little Desargues is going to follow, but how do we formulate this? The idea is that we can call this configuration the little Desargues configuration. So going forward, we have triangles in perspective from a point P that lies on a line L. This line L is the line determined from the intersection points of the first two pairs of lines, and then that guarantees the third intersection of corresponding lines also lies on L. Now, the idea is just like for Desargues, we flip it and we say we're going to say something about being in perspective from point P. The idea is we start with two triangles, and our assumption is that they intersect on a line L. Okay, so I have corresponding sides that intersect on a line L. Okay, the idea is that these intersecting on that line L, right, force this P to exist such that these triangles are in perspective from that P. Now, there's a little bit of a messy statement there, so we've screwed up a little bit, right? We haven't been as thorough as we need to be, right? Because what is it that we're actually saying? So if we take our two triangles and we start out with two sides, right? Two pairs of sides, sorry, that those intersection points determine a line L. If the third pair also intersect on that same line L, then there's a point, right? There's a point from which those triangles are in perspective from on L, right? This is the idea. Okay. Now, I saw that some of you that had turned in the homework already, I saw the problem here is that you you made a statement that made it seem like the point P in question could be like in any point on the line, and that can't be the case. So it's not can't be any point. It's that there's some point P on the line for which which these triangles are in perspective. Okay. All right. Okay. So note that this again is note how this is actually related to the converse of the Desargues theorem. Okay, so converse of Desargues says that they're in perspective from a point. This is saying something slightly different, right? So here I'm slightly restricted. But why does this actually follow from the normal little Desargues? The idea is exactly what I said, that if you actually follow through how we proved the converse Desargues theorem, you'll see that this proof, you can replicate this proof, except P is up here. That's it. Okay. That's it. If you're careful, basically you take this picture and you can move P to this line, L, and this basically spits out the proof of the little Desargues, or converse little Desargues. Okay, so that's the idea. Okay, so let's see. Let me make sure I got to these questions. Does the little scissors theorem mean if A, B, C, D, and A prime, B prime, C prime, D prime are quadrilaterals with vertices lying alternately on two parallel lines, and if blah, blah, blah? Let me think about your notation here for a second. I think that makes sense. So the scissors theorem itself, let me Yes, that's right. It's the same thing. The key assumption here is the key difference here is just like was true in the case of moving from Desargues to little Desargues, the difference was a moving of the point. So Desargues, the point was wherever. Little Desargues, the point was required to be on the